All right, in this explainer, we're going to peel back the layers on one of humanity's oldest and maybe most underrated materials. We're talking clay. From the most ancient pottery all the way to the coffee mug you're probably holding right now, we're going to find out what makes it tick, and I mean really tick, right down to the atomic level.
For literally thousands of years, we've been shaping, firing, and using ceramics. It's this amazing technology that stretches in an unbroken line from our earliest ancestors all the way to, believe it or not, the super advanced components inside our smartphones.
So, what is it about this stuff? What gives ceramics this incredible range of, well, superpowers? I mean, how can one family of materials be delicate enough for a teacup, but also tough enough for heavy duty industrial tools? That right there, that's the big question we're digging into.
Okay, so before we can uncover the secret sauce, we need to get on the same page. We've got to understand the material itself. So, first things first, what exactly is a ceramic?
Well, at its core, the definition is actually pretty simple. You take something that's inorganic, so not from a living thing, and non metallic. You shape it, and then you harden it by heating it up to some really high temperatures. You bake it. Sounds simple, right? But oh man, this simple process creates materials with some truly incredible characteristics. And it's this combination of properties that's just so wild. Think about it. Ceramics are super hard, but they're also brittle. They'll shatter. They can handle crazy high temperatures, which is why we call them refractory. They're fantastic insulators for both heat and electricity. And on top of all that, they're super resistant to corrosion and chemically really stable. It's this totally unique mix of superpowers that makes them so incredibly useful. Now, of course, for so many of the ceramics we know and love, from pottery to tiles, the story really starts with clay. And clay has this one secret weapon, this one special property that makes everything else possible. I mean, just think about it for a second. You add a little water to some dry clay powder, and boom, it transforms into this pliable, workable material. You can shape it, and it just holds that shape. It stays put. So what's going on here? What's the secret behind this almost magical ability? The official name for this is plasticity. And it's really the Goldilocks property of clay, you know? It's not too runny, not too stiff, it's just right. It's this amazing ability to be deformed when you push on it and then hold that new shape when you let go. That's the whole reason our ancestors could even make the first pots and bowls. Okay, but here's the thing, and this is the crucial part. This amazing property, it doesn't just come from the mud itself. Nope. To really, truly understand plasticity, we have to zoom in. I mean, way, way in. We're going to the atomic level. Yep, we're diving right down to the molecular level, because that's where the true secret of clay is hiding. And it's hiding in plain sight, built from these unbelievably tiny, repeating sheets of atoms. And this is where it gets really cool. All the incredible variety of clays we have in the world. I'm talking from the basic stuff you might find in your backyard, all the way to high-tech industrial ceramics. They are all built from just two fundamental shapes, two building blocks. That's it. So let's meet our two main characters. On the left, you've got the silica tetrahedron. That's one silicon atom surrounded by four oxygen atoms. And on the right, we have the alumina octahedron, one aluminum atom hanging out with six hydroxyl groups. These two simple shapes, they're the whole story. They are literally everything. Now, these little tetrahedrons and octahedrons, they don't just float around on their own. Oh no. They link up, they share atoms, and they form these vast, flexible sheets that are only a single atom thick. It's kind of like thinking about sheets of chainmail, but on a mind-bogglingly small, atomic scale. Right, so if all clays are made from the same two types of sheets, what makes one clay different from another? Well, the answer is as simple as a recipe. It's not about the ingredients, it's about how you stack them. And it turns out the stacking really only happens in two main ways. You can have a simple one-to-one pattern, right? One tetrahedral sheet connected to one octahedral sheet. Or you can have a two-to-one pattern, which is more like a sandwich. You've got an octahedral sheet tucked right in between two tetrahedral sheets. And believe me, this tiny difference in the recipe, it changes everything. Let's look at how this plays out with two real-world clays. So on one side, you have kaolinite. That's a 1-1 clay. Its layers are locked together super tight by strong hydrogen bonds. Water just can't get in between them, so it doesn't swell much and it's not very plastic at all. But then you have montmorillonite, a classic 2-1 clay. Its layers are held together by much, much weaker forces. So water can just rush right in, pry those sheets apart, and make the whole thing swell up. And that is what gives it its famous high plasticity. And this quote from the research really nails it. It says, "The individual crystals of montmorillonite clay are not tightly bound, hence water can intervene, causing the clay to swell." It's that simple. Because those bonds are weak, water can get in there and act like a billion tiny little wedges, pushing the sheets apart and giving the clay that slippery, moldable feel we know as plasticity. So this is all fascinating stuff, right? But what does all this atomic level knowledge actually mean for a potter, for someone with their hands in the mud? Well, it means everything. It means you can control it. Let's dig into how. See, because we understand these sheets and the forces holding them together, we can manipulate them. We're not just blindly mixing mud and water anymore. We can actually use chemistry to make the clay do exactly what we want it to do. It's like having a cheat code. So how do we do that? Well, one of the most powerful tools in the potter's toolkit is a process called flocculation. It sounds complicated, but in simple terms, it just means you're adding a substance that makes all those tiny clay particles start clumping together. And doing that can completely change the properties of a liquid, like a glaze. Okay, let's break down how this works. It's actually pretty clever. First, just imagine those tiny, flat clay particles are like a deck of playing cards, all floating around freely in the water. Now, you add a flocculant. This stuff releases positive ions into the mix. And these positive ions, they go and stick to the edges of the clay particles, which happen to be negatively charged. So now, suddenly the edges are positive. And what do those newly positive edges do? They get attracted to the big, flat faces of other clay particles, which are still negative. So they start sticking together, edge to face, building this sort of house of cards structure throughout the liquid. And that's what makes it thicken up. And this isn't just theory. This has a massive real-world impact. By doing this tiny little bit of chemical engineering, a potter can take a runny, watery glaze that would just drip everywhere and turn it into a thick, creamy one that coats a pot perfectly, nice and smooth. It is direct control, and it all comes from understanding those atomic sheets. So, there you have it. We've gone from a simple coffee cup all the way down to the atom and all the way back up again. It really makes you wonder, doesn't it? If we can understand the fundamental building blocks of materials this deeply, whether it's clay or carbon or something totally new, what else can we build? What other incredible things can we design and create? What's the next material whose secrets we're going to unlock?